In this video, we briefly introduced the polarization of lights, polarizing filters, and polarization by reflection and scattering. The polarization of an electromagnetic wave refers to the orientation of the electric field portion of the wave rather than the magnetic field portion. So in this little animation, we have vertically polarized light because the electric field is vertically oriented. But the light we find in nature, sunlight for example, is ordinarily unpolarized, meaning there's a mix of all different polarizations in the light. We can represent this by showing the light ray with little electric field vectors going vertically and horizontally. So both components are present in the light ray. I do want to point out here that the oscillation of the electric field is always perpendicular to the direction of propagation of the wave, because electromagnetic waves are transverse waves. But I have many different orientations I can choose for the electric field that are perpendicular to that propagation direction. So this diagram of the different possible components of the electric field vector can be viewed edge-on for the purpose of working a variety of physics problems. And from that view, it looks like the second picture, with one component of polarization in the plane of the page that's going up and down in this picture, and one component pointing in and out of the page, and that's represented by the white dots in this picture. So the most common way to end up with polarized light is to use a polarizing filter. And a polarizing filter is made of long chains of molecules all lined up in the same direction in a film. And these absorb light when the electric field is moving along their axis. The idea is that electrons can be moved along these molecule chains by the electric field in that orientation, and that energy is then dissipated as heat. Light waves moving perpendicular to these molecule chains will pass through with no problem because they can't excite the electrons up and down the molecules. On the other side of the polarizing filter then, one orientation of the electric field is missing and we end up with a polarized ray. So in the picture on the right, I'm coming into the polarizing filter with both components of electric field present. There's the up and down and the in and out. And I'm showing the polarizing axis of this polarizing filter. The molecule chains are vertical. So light that's horizontal passes through, but light that's vertical gets absorbed. And on the other side of the filter, I see horizontally polarized light. Light can also be polarized in nature, and one way this happens is by reflection. So we're going to consider a light ray reflecting off of an interface so that the angle between the reflected and refracted rays is exactly 90 degrees. Now this is a very special circumstance, but we're going to generalize the result after we figure this out. Something very special happens for this particular arrangement. The reflected light is polarized in the horizontal direction. To see why this happens, we look at the light ray entering the interface at this point, and we're showing the different components of the polarization in the incoming ray when it hits the surface. When the light strikes the interface, the reflection and refraction both propagate by the excitation of molecules in the material, which then re-radiate the light as it propagates. When we think about the molecules at the point of contact, the light in the horizontal polarization causes molecules to oscillate in and out of the page. This is no problem for the propagation of light in the reflected and refracted rays, since those rays are propagating perpendicular to the direction of oscillation of the dipoles in the material. Recall that the intensity of radiation coming off of an oscillating dipole is maximized in the direction perpendicular to the oscillation, and that's what we have here. And I'll post a link real quick to the video where this idea was first introduced. However, when we look at the other component of polarization, something special happens. Molecules at the point of contact are oscillating back and forth with this orientation. And while that isn't a problem for the refracted ray, because that oscillation is still perpendicular to the ray direction, it is a problem for the reflected ray. The oscillation of the dipoles is parallel to the direction of propagation of that ray, and there can be no radiation in the direction parallel to the dipole oscillation. Thus, the reflected ray has one component of polarization deleted, and the reflected light is horizontally polarized. The special incident angle at which this occurs is called the Brewster angle. I'll call that theta b. But any reflection will produce at least a partial polarization of the reflected ray parallel to the surface. For example, if we're a little steeper than Brewster's angle, the oscillating dipoles for that particular component of polarization will be nearly parallel to the reflected ray, and the radiated intensity of a dipole oscillating nearly parallel to the direction of propagation is much less than when it's perpendicular. So just a quick note on practical applications. This is how polarized glasses work. Polarized glasses include polarizing filters in the lenses that only allow the vertical polarization to pass through, and they kill off the horizontal polarization. So these are very effective at reducing glare off of the water or off of a road. Notice though that polarized glasses do nothing to stop the glare off of a window, since the reflection off a vertical surface results in vertical polarization of the light. Let's look at a couple quantitative examples with the Brewster angle. So in the first one, we want to compute the Brewster angle in general for polarization by reflection for light at the interface of materials with index of refraction N1 and N2. So the first thing I do is apply the law of reflection, and I realize the reflected angle is equal to the incident angle. And then I'm going to label the refracted angle. And I notice right away that theta r plus 90 degrees plus theta b is equal to 180 degrees. Those add up to a straight angle. Subtract 90 from both sides, and I get that theta r plus theta b. Now we also want to relate the refracted angle to the Brewster angle, and we use Snell's law for this. And since the goal is to solve for an expression for the Brewster angle, I want to replace this refracted angle with an expression in terms of the Brewster angle, and I'm going to use 90 minus the Brewster angle for that. To simplify the sign of 90 minus an angle, I use a trig identity. The sign of a difference of two angles is going to be sine of the first, cosine of the second, minus cosine of the first, sine of the second. And our first angle here is 90 degrees. That's A in the expression. So the sine of A is going to be 1, sine of 90, and the cosine of A is going to be 0. So that whole second term dies. And I'm left with just the cosine of B, so the cosine of the Brewster angle. So I can rewrite my equation as N1 sine theta B equals N2 cosine theta B. Then I divide both sides by the cosine, because that gives me a tangent on the left-hand side. I'll just clean that up right now. And at the same time, I divide by N1 on both sides. So I have an N2 over N1 on the right-hand side. So this means the Brewster angle at the interface between two materials is given by the inverse tangent of N2 over N1. So let's try it with a light ray that's reflecting off of water. We're told that the index of refraction of air is about 1, and for water, it's about 1.33. And I simply plug into my general solution for the Brewster angle. And when I run the numbers on this to 3 significant digits, I get 53.1 degrees. So that's the incident angle that gives you perfect horizontal polarization of the light. But keep in mind, any angle reasonably near that is going to have quite a bit of horizontal polarization. So polarized glasses make a big difference without the angle being exactly perfect. Another way we can get polarization in nature is by scattering. As sunlight hits the atmosphere, it causes molecules to wiggle back and forth with the oscillating electric field in the sunlight, and these molecules re-radiate or scatter the light. Incidentally, the intensity of the re-radiated light is greater for higher frequencies, and this is actually why the sky appears blue. So there's a special direction in the sky, 90 degrees from the direction of the sun, where we can see highly polarized light. So in my first picture, the stick figure, they're shading their eyes as they look up at this spot in the sky. And from that person's perspective, the sun is this way. The spot in the sky they're looking at is 90 degrees away from that. So in the second picture, we look at the sunlight, but with both components of polarization at this spot the person is observing. And if I look at the in and out of the page polarization, that's going to cause molecules to wiggle in and out of the page right here. That's a perpendicular direction to the direction of this scattered ray coming to the person's eye. And that's no problem. The dipole is oscillating perpendicular to the direction of propagation of the ray, and it radiates with maximum intensity in that direction. The other component of polarization, though, is a problem. When I have a molecule wiggling back and forth in this direction, and again, this is only perfectly aligned because of this 90-degree difference between where the sun is and where the person's looking, that molecule is wiggling back parallel to the direction of propagation of the scattered ray, and an oscillating dipole can't radiate in the direction parallel to the oscillation. So again, we have an entire component of polarization killed off, and this person is going to see light that's polarized only with this component that's going in and out of the page in this diagram. So I encourage you to get outdoors and try this. You locate the direction of the sun in the sky. That's easy enough. And then look at a spot in the sky approximately 90 degrees from the sun. And then just rotate your polarized glasses back and forth, and you'll see a dramatic darkening of the sky. Note that photographers use polarizing filters to darken the sky, and this increases contrast with the clouds, for example. The clouds are reflecting unpolarized light from other parts of the sky, and you can darken the sky behind the clouds by using the polarizing filter and make the clouds appear brighter than usual. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.